Hey everyone, welcome back. I hope you're doing well. Hope you stayed warm over the weekend. Unfortunately, I can't be here with you today, but just like days that you're going to be away, we need to keep this course moving. Lots to cover and a short amount of time in the semester. Today, things we're going to need are a periodic table, your student booklet starting on page 21, and a scrap of paper that we're going to use first. Be sure to check your calendar on the website if you're absent any day, just to see what material you missed and tutorial videos to help with concepts. On Wednesday, we're going to be doing a Bohr diagram assessment, and that'll just involve coming in and picking an element and drawing a diagram of it like we were working on Friday, and we'll do some more work with today. So we're going to start by doing a Bohr diagram review. We did a bit of Bohr diagram drawing practice on Friday. Niels Bohr was one of the atomic theorists that we looked into on Wednesday. He's credited with the planetary model. It's not the current most up-to-date way that we view the atom, but it's a useful way to draw the first 20 or so elements and what their electrons look like. We're going to start by drawing calcium, and we need to know a bit of information before we start: the amount of protons, electrons, and neutrons, because we're going to illustrate those in our model. We remember that the amount of protons is the atomic number, and so the amount of protons is 20 for calcium, and that's the same with the amount of electrons. Sometimes the neutrons will be the same as the protons, sometimes they'll be off by 1 or 2, so we have to take the atomic mass and subtract the amount of protons. We do that because the mass of an atom is mostly because of its protons and neutrons. So 40, we'd round down to 40. 40 minus 20. This case, we do have the same amount of neutrons as well, but that's not the case every time. So our first step when we're going to start our model is to make a circle to represent the nucleus. Inside, you're going to communicate how many protons and how many neutrons are in your atom. So the rules for drawing your electrons, we really need to focus on the first 3 levels. The first level has 2. And your second and third level have 8. I've written that your fourth level contains 2, and that's mainly because the Bohr diagram model isn't really useful after the 20th element, which happens to be calcium here. So our first level is 2 electrons. You'll notice my circles aren't the greatest, and yours don't need to be either. One way that helps it stay a little cleaner is if you, especially when drawing your shells of 8, double up so you have pairs. So now I've filled that second shell, so I'm going to need to draw a third one. I've drawn 10 electrons in total so far, and so I have another 10 to go. So I know I'm going to fill this one as well. And I have one more to draw. And in my last shell, second last shell, excuse me, no, last shell, I have 1, 2 to draw. So I've drawn my 20 electrons, I've communicated 20 protons and 20 neutrons in the nucleus. One last thing we're asking you to do is called a charge balance. And so that is taking all of your positively charged particles and subtracting from them your negatively charged particles. So in this case, of course, I have 20 positives, 20 negatives, 20 negative electrons, and that's going to make my charge 0. That makes this a neutral atom. And shortly we're going to explore what that means a little further. What I'd like the instructor to do at this time is pause the video, and that'll give you a chance to try phosphorus on your scrap of paper. So phosphorus is atomic number 15, which means it has 15 protons, 15 electrons. Let's see how many neutrons it has. The atomic mass is 30.97, which is pretty much 31. So if the mass is 31 and I have 15 protons, that means that I have 16 neutrons. So to draw this, it's going to be a little easier to draw than calcium. I have my circle for my nucleus, 15p, 15, 16n. First level has 2. Yikes, that was an awful circle. Second level has 8. So that makes a total of 10. So I have 5 more electrons than I need to draw. I'm going to draw one last circle here. And 1, 2, 3, 4, 5. So in total I have 2 plus 8 is 10, plus 5 is 15. I would write that I have 15 positive particles, 15 negative particles, total of 0, and again, this would be a neutral atom because it doesn't carry a charge. Last thing we want to mention is a reminder about valence electrons. Valence electrons are the amount of electrons in an atom's outer shell. And so if we look to our first one, calcium, in calcium's outer shell it has 2 electrons, so that it would have 2 valence. The amount of valence electrons something has will kind of dictate how reactive it is. This is one of the reasons why the periodic table is grouped the way it is. The groups share the same amount of valence electrons. Just to do phosphorus as well, phosphorus has 1, 2, 3, 4, 5 valence. So when we get to the assessment, you'll kind of get a list of different things we want to see. Some of them will be the listing of protons, electrons, and neutrons, the charge balance, of course your drawing itself, and then you'll be asked how many valence electrons there are. So just taking a look back to the work we did on phosphorus, one of the things we identified was its overall charge. And phosphorus's overall charge is 0 because it has 15 positive protons and 15 negative electrons. So in one way, it's kind of balanced. But in another way, it's not balanced, and that's in its outer shell of electrons. Electrons want to follow something called the octet rule, meaning they want to go to the nearest full shell. So some elements, it will be easier for them to lose electrons to get to the nearest full shell. That would be the one like calcium, because it's easier for calcium to lose 2 than gain 6 to get to the next 8. And the opposite is such for phosphorus. Phosphorus has 5 electrons on its outer shell. its electrons want to get to a full 8, so it will gain 3 electrons from another atom or another element to find that stable outer shell. This is why the noble gases in group 18 they don't react with other elements, and it's because they have a full outer shell. Helium's a little different because it has a full outer shell of 2. Remember that the first shell only has 2. And then neon and argon, they won't react with any element because they have a stable electron shell. The other elements want to be like, the other atoms want to be like neon and argon and helium and the noble gases. So the other elements will lose or gain electrons so that their outer ring can have a full 2 or more likely a full 8. So we have some terms. We have some terms for that. When a metal, all the metals share a property that they will end up losing 1 or more electrons. And when they lose an electron, they're losing a negatively charged particle. That makes the overall charge of that atom positive. This is called ionization. Ionization is where a neutral atom can gain or lose electrons to get to the nearest full shell. This creates a stable electron shell like noble gases, but it does something to the overall charge, the overall electrical charge of the atom, and we call that becoming an ion. So I'll draw sodium here, and then I'll draw what happens to sodium when it becomes an ion. Sodium is atomic number 11, which means that it has 11 protons, 11 electrons, and we have 22.99, which is pretty much 23 for our mass. 23 minus 11 would make 12 neutrons. So if I'm drawing sodium, I'm going to have my first circle, and that's going to contain 11p, 12n. One thing I didn't mention yet was that we're going to do this drawing on page 21. You'll notice there's 2 spaces to draw the sodium atom becoming an ion. And then with the same with chlorine, our next example. So I have 11 electrons to draw. First level gets 2. Second level gets 8. And that's going to make a total of 10. So I'm going to have 1 more electron. So sodium has this 1 more electron, a sodium atom. And so we would say that it has 1 valence electron. And now to get to its nearest shell, it's pretty easy for a sodium atom because it just has to lose 1 electron. That's one of the reasons why the atoms or the elements in group 1, like sodium, are so reactive. It's because it's so easy for sodium to just lose 1 electron to another element. So the sodium will lose that electron, and we will do a drawing of what that looks like. 11 protons, 12 neutrons. Same thing, it's going to have the 2 on the first level, and then it's going to have 8 on the second, and now it's lost that electron to another atom. So we can do a charge balance on each of them. On the atom, we have 11 protons, which are positive. We have 11 electrons, which are negative. That's going to be a 0 charge. When it becomes an ion, we still have 11 protons. That never changes, but we lose an electron to something else. So we now have 10 electrons. So the overall charge becomes plus 1. When I lose a negative particle, that takes my overall charge to be a plus 1. So we communicate this by calling it an ion. This is now a sodium ion. We also communicate it by putting the charge above it. And we don't have to write plus 1. We just write a plus, and that means plus 1. So again, I'd like your teacher to pause the video here so you can try to draw chlorine. We want you to draw chlorine, the atom, with 17 protons, electrons, and then draw the ion. One thing we'll mention to you is it's going to be a little different than the sodium atom. So the chlorine atom is atomic number 17, which means protons are 17, electrons are 17, and neutrons, 35.4 would round down to 35, and 35 minus 17 would be 18. So if I'm going to draw chlorine, I'll just zoom in a bit. My chlorine is going to have 17 protons and 18 neutrons. I just need to now draw the 17 electrons. First level has 2. Second level has 8 to make 10 in total. Third level has 2, 3, 4, 5, 6, 7. So you'll notice chlorine is 1 electron away from having a full shell. And chlorine's one of the halogens in group 17, and they are the most reactive nonmetals. And the reason they're the most reactive nonmetals is because they just need 1 electron to be a full shell. So they'll rip that electron from any number of elements. So to draw what this looks like as an ion, I'm just going to move this over. I'm going to cheat a bit and copy it. And so chlorine will pick up 1 extra electron that I've drawn here in red. And when it does that, it's now changed the charge balance. So I'll do a charge balance for both. The atom has 17 protons, positive, 17 electrons, negative, for an overall charge of 0. When I gain an electron, I'm gaining a negative particle, so my protons stay the same. My electrons I've increased to 18. That makes my overall charge minus 1. So now I have an electrically charged negative particle, a chlorine ion. We call this chloride, and we'll get to the naming in a couple of days, but just to mention it. And we communicate that this chlorine has a -1 charge by putting that negative symbol above the Cl. Whenever I see a positive or negative symbol, and you might see a number beside of it, if it's maybe -2 or -3, that means we're talking about an ion. That means it's either gained or lost electrons. The next thing we're going to have you do is a bit of independent work on page 22. We're looking for you to do both sections. So we just did some drawings to illustrate what happens when an atom loses or gains electrons to become an ion. We're just looking for you to kind of fill in this table when you identify that something is an ion or a neutral atom. So the first one's the same as the one in your booklet, and then the other ones are a little different. So we have a lithium plus sign, and that plus is a sign that we're dealing with an atom. That plus sign is also a sign of its charge, and because it's just a plus instead of plus 1 or plus 2 or plus 3, the ion charge is plus 1. Lithium is atomic number 3, which means it has 3 protons, and because we have that plus sign, that means we have one more positive particle than negative particle. So that means that we must have 2 electrons. So just to repeat how we figured that out, because we have a plus sign, it means that we have a difference in our positively charged and negatively charged particles. And a plus sign means we have one more positive than negative. The number of protons will stay the same in an ion or an atom because that's the number of protons is what element it is. So when we have a plus, one more positive than negative. Looking at the next one, we have 6 protons and we have 6 electrons. We have a charge of 0. This means that we're dealing with a neutral atom, but we would have to look to the periodic table to decide what atom that is. And when we look at the periodic table, protons equals atomic number, so this equals carbon. This equals carbon. The next one is an oxygen with a -2 symbol. That means that it has a -2 charge. Oxygen is atomic number 8, so that means it has 8 protons. It has a -2, so that means that it must have 2 more negative particles than positive ones. And if it has 8 positive ones, that must mean it has 10 negative ones and a charge of -2. The last one, it tells us the charge, which means it's an ion because it has a negative charge, it's not a 0. And it tells us the amount of electrons. If something has a -2 charge, that must mean it has 2 more electrons than protons, 2 more negative particles than positive particles. So if it has 18 negative particles, then it must have 16 positives. And I grabbed that information because it has a -2, which means 2 more negatives than positives. I just have to remember what is atomic number 16. And atomic number 16 is sulfur with a charge of -2 as well. So take the next maybe 20 to 30 minutes to complete those sections. Just to wrap things up and kind of show us where we're going, uh, ions are one of the main ways that compounds form. To use our example that we've looked at today, when sodium gives an electron to chlorine, they both get a charge. Sodium a positive one because it now has one more proton than electrons. Chloride now a negative charge because getting an electron gives it one more electron than protons. And since opposite charges attract, there is an attractive force that pulls them together and they become a compound. If you were able to look and zoom in on the salt in your salt shaker at home, eventually, if you could visualize it, you would get down to this level where you see an attractive force pulling a sodium and chloride atom together. One last example to show you, beryllium and fluorine, if they were added together and made a compound, beryllium has 2 valence electrons because it has 2 on its outer shell. Fluorine has 7 valence electrons. So beryllium wants to lose the 2 to be balanced, and fluorine wants to gain 1. So beryllium can give 1 to fluorine. I'll mark an X to say that it's gone. Now beryllium has 3 electrons, but it's not happy yet. It has to lose 1 more. But it can't give it to this particular fluorine atom because this fluorine atom now has 8 valence electrons, meaning it has a full shell. So what it will do is it will find another fluorine atom to give this other extra electron. So now that's gone. So when beryllium loses its 2 electrons, it has 4 protons, 2 electrons. So it has an overall charge of +2. Fluorine, of course, just gains 1, so it would have 9 protons, 10 electrons for an overall charge of -1. And the same would be for this one as well. 9 protons, 10 electrons for a -1. So the +2 electrical charge of beryllium is balanced by 2 -1 fluorides taking electrons from it. We communicate these ratios when we're naming and using the formulas to write the symbols for our compound. And the way we would communicate it is beryllium, we would say that there's 1, and then fluorine, we would say that there is 2. So these are the chemical symbols to identify how many fluorines and how many berylliums would be in a compound of beryllium fluoride. But that's for us to dig into tomorrow. So thanks for your participation today. I'll have instructions for one more practice drawing for you guys to do.
In today's video, we're going to take a look at ionic compounds, with a focus on how they're structured, what their properties are, and how we can determine their formula. If you remember ionic bonding, it generally involves a metal atom, like sodium, transferring 1 or more electrons to a non-metal atom, like chlorine, to form 2 oppositely charged ions. And these 2 ions will then be attracted to each other by electrostatic forces, forming an ionic bond. And we call the entire thing an ionic compound. In real life though, ionic compounds generally involve tons of ions, not just a couple like we showed at first. And the positive and negative ions alternate, so that each ion is attracted to all of those around it. And as this happens in all directions, it would actually form 3-dimensional structures that we call regular lattice structures. So in our drawing here, the green ions represent the positive sodium ions, and the red ones are the negative chloride ions. We can also represent these ionic compounds with ball and stick diagrams, where we show the different ions and put lines between them to represent the ionic bonds. Next up, we need to take a look at the properties of ionic compounds. Specifically, that they have very high melting and boiling points, and that they can conduct electricity, but only when they've been melted or dissolved in water. If you think about any substance, the melting and boiling points are determined by the strength of the bonds holding that substance together. In ionic compounds, there are loads of ionic bonds, all of which are really strong. So to break them all would require loads of energy, which is only going to be available at very high temperatures. When it comes to conducting electricity though, the important thing is whether there are any charged particles that can move. and these could either be ions or electrons. When ionic compounds are in their solid form, everything is fixed, so they can't conduct any electricity. However, when they're melted or dissolved in water, the ions are free to move about, and this movement of charged particles allows them to conduct electricity. The last thing we need